We are in 11.5. I'm going to pick up talking about Alex and Gabriella. If you recall, Alex claims he's 75% free throw shooter. He shoots for Gabriella. He makes 30, only 30 out of 50. Gabriella notices that's 60%. Alex points out, oh, that's just due to natural variability. In other words, you're allowed to have an off day, he says. Whereas Gabriella's thinking, yeah, but is that too far off? So our job is to work through, some ideas, some processes as, okay, how could we decide is 60% within a reasonable range, or is 60% without, or is it outside that reasonable range? Okay, so we had looked here, and I had started talking about the idea of you could use Excel, you could use a calculator as a random number generator. Okay, where you can set that up. Now, with that in mind, that's what they did here. Okay, so the question is, how can you use random numbers to investigate Alex's claim? Okay, so we talked about the blue numbers. I'm gonna circle the blue ones because there are less of them to kind of differentiate here. Because I know you guys don't have blue, but what are they? Darker and lighter, maybe?
Not really.
Not even really?
A little bit.
Okay, so I would definitely circle one set or the other then on your paper. Just, And see, mine are all circled in two different colors, so I can't even really tell, lighter, if they're lighter versus darker or not. But okay, so they've kind of given you that idea, okay? 1 through 75 is one color. 76 through 100 is another color, okay? So we talked a little bit yesterday. How can we use this to decide what his percents are here? Okay, 1 through 75 is going to represent what? Each time a number is somewhere between 1 through 75, that's going to represent him making the basket, because he's claiming he has a 75% chance of making. So 1 through 75 out of 100 is a 75% chance. So all these orange numbers represent makes. The blue numbers, 76 to 100, then are going to represent his misses. And this is just random number. Now, obviously, there's actually a little bit of skill that goes into shooting, right? But this is, random numbers here. So, with that in mind, okay, that's the idea. And so what I'm going to do is I'm going to write out kind of that basic idea, generate random numbers 1 through 100, 1 through 76, or 1 through 75 represents makes, 76 through 100 represents misses. With that in mind, what is his percentage here based on this random simulation? How are we going to figure that out? What is his chance of making it according to this one simulation? What do you need to do to figure that out? What? Okay, are we doing some counting up? Now, reverse that though. Not 11 out of 50. No. There's 11 what? Misses. So if there's 11 misses, we're trying to find his percent of making it. So how many makes are there? There's 39 makes. In other words, there's 39 numbers 1 through 75. So 39 of these numbers out of 50. What is 39 out of 50 as a percent? Grab the calculator if necessary, of course. 78%, right? 39 out of 50 is 78%. Now, with the idea of 78%, well, that would verify that there is a chance he's a 75% shooter, yes. But this is what? One simulation, yes? Just like Gabriella witnessed one set of shots, right? Okay, this is one simulation of 50 shots. Gabriella witnessed one set of 50 shots. Is that enough information? Not really, okay? And this is where we'll go down in here and talk about what if we keep doing this over and over and over. Remember yesterday with Seth and Tia. One set of information from Seth, one set of information from Tia. Was that enough? No, then we start talking about their whole class. That becomes, more information. The more information you get, the better. So, how can you use random numbers to investigate Alex's claim? Okay, I'm going to say use a random number generator. That can be something on a calculator. That can be something on like Excel, for instance. Generate numbers 1 to 100. Okay. Assuming he makes 75%, then we're going to let 1 through 75 represent makes, if you will. And then 76 through 100 are misses. Okay. Based on the information we came up with here, there are 39 out of 50 makes, and 39 out of 50, you guys did the math and you told me it is 78%. Okay, or I guess really 0.78, which of course is 78%. And then the argument's always going to be, though, that's one trial. Okay, so I'm going to go on to say that just like one set of shots wasn't enough, one simulation is not enough. Now, if we just go off of this one simulation, that supports Alex, doesn't it? Because that actually puts him above 75%. Okay, now on this bottom piece here, it talks about a sampling distribution. Okay, sampling distribution is the distribution of sample statistics from different samples of the same population. And it's asking us how we can interpret the sampling distribution. The idea is, up above, this was one simulation. Okay, one's never going to be enough to prove a point. Okay, the more data, the better is always going to be the idea here. So now you've got a frequency chart here, or a histogram, I guess I should say. As you look at this histogram, we've got lots of trials. You know, there's in this first, there's what, 3 that had 30. Looks like there's 2 at 31, 3 at 32. Over here, it looks like there's 16 that had 38 shots. Now, keep in mind this is out of 50 trials, so you know that's 30 out of 50 all the way up to 44 out of 50. And if you add these up, if you add up how tall each bar is, this represents 100 samples. It doesn't tell us that, but there are 100 samples here. 100 samples as opposed to one sample. Is that going to make information a little more valid?
Yeah.
Yeah, because, so, and this is not him shooting 50 shots 100 times. Which could be done over a course of time, right? But this is running a random number generator, getting your 100 numbers, or getting your 50 numbers 100 different times. Okay? Now, with that in mind, okay, remember yesterday I was talking about the 50% data a lot. Or not 50% data, excuse me, the 95% data. That 95% of your data, you know, that's going to be the bulk of the data. And that's going to be what we're looking at in this lesson. Well, as you look at 95% of the data, well, first of all, do we see a little bit of a normal curve here? The general shape, right? It's not going to be exact in these scenarios, but you see a little bit of the shape here. If we're looking at 95% of the data, folks, there's 100 samples here. So basically, we're looking at all but 5 of those samples. If you look at all but 5 of those samples, you know, what are we taking off? We're taking off either end, okay? And here's another thing. Where's his 75% claim fall? Falls right there in the middle, doesn't it? Okay. But if we do that, if we take off all but like the 2 ends, then we're looking at something from there to there, give or take. Okay. I mean, I definitely think you could take off the lowest and the highest. With that in mind, okay, if we look at that middle 95%, we're looking at, what's the lowest we're looking at then? We're looking at 31. And what would 31 out of 50 be? 31 out of 50 would be 62%. Okay. What's the highest we're looking at then? 43. And what would 43 out of 50 be? 86%. Okay. So what's this data going to support? This data is saying, okay, if we do this simulation 100 times, and we're looking at that middle 95% of the data, if he claims he's a 75% shooter, he should realistically fall in what range? 62% to 86%. Okay, in other words, if he is truly a 75% shooter, he should be expected to fall in that 62 to 86% of the range 100% of the time. Where did he physically shoot? 60%. So are we going to support Alex or Gabriella based on this data? I'd be supporting Gabriella. That, okay, you can claim natural variability. I can't say that word very well. Okay. However, 60% is kind of on the low side. It's not much low, is it? But it is definitely right there at the outskirts. Okay. So that's a way to use random numbers. Now, I'm going to write down some information. And I'm going to start with the fact of 95%. Okay. So 95% of the data falls within, what was it, 31 to 43 successes, or 62 to 86%. Okay. So based on this simulation, a reasonable range for a 75% shooter is 62 to 86%. Thus, Alex is likely not a 75% shooter. Okay. you're not going to be doing random simulations. Okay, that's not something you're going to be, they have us worrying about doing. Might still be something I show on the calculator at some point, just because it's kind of a fun thing. Just like I might show standard deviation on the calculator at some point. But be able to follow the idea, answer some questions. Okay? Now, we have 2 follow-up questions on the next page.
You just dropped it and no idea where it went.
I actually thought it was Lily's at first, then I realized, no, it's yours. You just lost track of it. Okay, next page. If you look at the next page real quick, top of the next page that is. Now, how would your conclusion differ if you did 100 simulations of 10 shots each? So what did we have last time? We had 100 simulations, yes? But it was 50 shots. Okay? So the difference is 10 shots. How's that going to change things in terms of, we don't know how it's going to change things in terms of what are the exact results going to be. But what's different there? There's less shots. So what's going to say about the data in general? Less shots is probably going to make the final data more or less accurate? Less accurate, right? Because the more data you can get, the more accurate we're going to expect. Because this is 10, so because the sample size is smaller, is 10 shots instead of 50 shots, it'll make the results less accurate. Okay. That's all I'm going to put here is the smaller sample size of 10 instead of 50 makes the results less accurate. Look at the next question. How would it differ if you did 100 simulations of 1,000 shots each?
That's a lot of shots.
That's a lot of shots.
Accurate.
And a lot of shots is going to make it more accurate. Okay, the more data, the better. So larger sample size will increase accuracy. Okay. All this leads up into margin of error. Now, I asked you to have a calculator at your desk, right? This is where you're officially going to need the calculator because we actually do a little bit with numbers. I learned you guys kind of miss it when we don't use numbers very often, so maybe you'll like the numbers. So the idea of margin of error, okay? According to the empirical rule, 95% of values in a normal distribution fall within 2 standard deviations of the mean. So 95% of all sample results fall within 2 standard deviations of the population parameter being evaluated. Okay, thus I keep talking about 95% in this lesson, right? Okay. Now, the idea then is the margin of error gives the maximum expected difference between the sample result and the population parameter. So that margin of error is going to give you the idea that, for instance, the 75% claim. That margin of error that we kind of ended up with is, okay, his margin of error would be 62 to 86%. Okay, like that's kind of the range of reasonable results. And that's what margin of error gives us for. Now, we have two different formulas, and it's going to be dependent on the situation of which formula you use. We have the quantitative data formula, and you'll notice the margin of error formula is 2 sigma over the square root of n. Remember what's sigma? Standard deviation of a population, and n is just the sample size. Now, so a quantitative margin of error, remember we previously in this chapter talked about quantitative versus categorical. Quantitative means your data is going to be based on numbers. Okay, there's going to be numerical, the statistics are going to be based on numbers. Okay, as opposed to categorical data. With categorical data, it's more of a which category do things fit into. Maybe numbers are involved, maybe numbers aren't involved. Okay, but the margin of error for categorical data is 1 divided by the square root of n, where n is the sample size. Okay, now sometimes it's very obvious which formula you use because, I'll be honest, when they give you standard deviation, guess what? You're going to be using the quantitative formula. If they don't give you standard deviation, guess what? You can't use the quantitative formula. You have to use the margin of error. Unless there's a way to find standard deviation. But usually in this problem, they either give it or they don't. Okay, so there's my hints to you. So let's look at a couple of examples here. Okay, SAT is back. Can't get away from it, can you, juniors? The College Board recently reported that the mean score on the SAT mathematics exam is 508 with standard deviation 121. Familiar, huh? Washington High believes that its seniors score considerably higher than the national average, so the school randomly selected scores from 200 seniors, finding a mean score of 550. Is Washington High correct in its belief? Okay, in other words, Washington says our seniors had a mean score of 550. We think that is considerably higher than the national average. Now, the exact average is 508, right? But what we want to know is, okay, there's that margin of error. Do they fall above that margin of error? Okay, so we're going to find the margin of error and look at that scenario. What do you think? Is this going to be quantitative, based on numbers, or categorical, based on categories? There's data involved here, yes? Okay, well, there's always going to be data involved, but we have a mean and a standard deviation based on the data there. Okay, so this is going to be a quantitative problem. Quantitative. Sorry. That type of word is a spelling nemesis to me. I don't know about you guys, but. So, the formula for margin of error. Let's start by finding the margin of error. And my quantitative formula is that 2 sigma over the square root of n. Okay, well, 2 is 2. I'll give you that one. What's sigma? 121, because remember sigma is standard deviation. So 2 times 121 divided by the square root of n. N is 200 because it's the sample size. Who did they poll? They polled 200 of their seniors. 2 times 21 divided by the square root of 200. 242 divided by the square root of 200.
17.1119.
Okay. And I was waiting to see, because I just have 17 point weirdly written down on my paper, so I was trying to wait and see. Here's the deal. Our mean was given as a whole number, yes? So with that in mind, I'm going to use my margin of error as a whole number. And you'll see why here in a moment, because we're going to put that mean and that margin of error together. Okay, but I'm doing that because my mean was given as a whole number. Because here's the deal, I want a range. This is my margin of error. So the idea of margin of error is says, okay, that margin of error then can go 17 below or 17 above. 17 above and below what? What's the middle?
508.
Our mean, which is 508. Or if you remember mean, mu. Okay. So what I'm going to look at here is I'm going to look at the mean plus or minus the margin of error. Okay. So my mean is 508 plus or minus what do we find as our margin of error? 7. Now turn that into a range for me. 508 plus or minus 17. Turn that into a range. As in, what is 508 minus 17? And what is 508 plus 17? 508 minus 17 is 491. What is 508 plus 17? 525. Okay, this right here is my range of reasonable means. I think they use, yeah. So this right here is your basically range of reasonable values. But I'll be official, range of reasonable means. Now, we have to go back and answer the final question. Is Washington High correct in its belief? Its belief, Washington High believes that its seniors score considerably higher than the national average. What did their seniors score? Their seniors score 550. Did they score considerably higher than the national average? They scored above that range of reasonable values, didn't they? So with that in mind, Washington High is correct in their belief. Okay? So my answer key says yes, Washington High is correct because 550 is above the range. So yes, Washington High is correct because 550 is above the range. Obviously, you need the work to get there, but that's your official final answer. Okay? Are we okay with that? We had to do a little math, but we still used words, right? Okay. Now, let's go down and talk about, we're going to talk about SAT a little bit more. A random sample of 100 Washington High seniors reveals that 40% plan to take the SAT this year. Use the margin of error to predict the actual proportion of seniors planning to take the exam. Okay? So this problem's separate from the last problem in a way. Okay? I mean, yes, we're still talking about Washington High, but this is separate. A random sample of 100 reveal that 40% plan to take the SAT this year. Margin of error to predict the actual proportion of seniors planning to take the exam. So 40%, now, that's a random sample. So is that going to be the exact number that take it? No, we're looking for that, what's that range of reasonable values? So, how are we going to find the margin of error? Okay, this is categorical because here we're just talking about the seniors. We're talking about the category of seniors and taking there. We don't have a standard deviation, a mean and standard deviation of seniors. This is a category. It's a percent for their category. So this is categorical. So based on the category of seniors. And we're going to find the margin of error. What's the margin of error formula now then? Okay. 1 over the square root of n. So 1 over the square root of, what's n? N represents the sample size. What is the sample size here? 100. So 1 over the square root of 100. What is the square root of 100? 10. Now, what is, so 1/10, based on the fact that they gave me a percent, let's change 1/10 into a percent in this scenario. What is 1/10 as a percent? It's 0.1. You move the decimal 2 places right, and it is 10%. Are we okay with that? Now, the question is, use the margin of error to predict the actual proportion of seniors planning to take the exam. They sampled and said 40% claim. How are we going to make that what's the margin of error going to say then? What's going to be that range? We're going to have to look at that middle 40% and then what? Plus or minus that margin of error of 10%. So that margin of error of 10% is 10% below and 10% above. That's margin of error every time, below and above. So what is 40 minus 10? 30. What is 40 plus 10? 50. So 30 to 50% of seniors plan to take the SAT this year. Now, in Savas, may they just ask for margin of error? They might. But when they start asking for a range of reasonable values, you're taking that margin of error and adding and subtracting it from whatever the given value was. Okay? Okay, 2 last questions. Still about margin of error, but we're done talking about SAT. Okay. Find the margin of error for a sample with a standard deviation of 54 and a sample size of 450. That's all they tell me. Which formula are you guessing we're going to use? Quantitative, right? Or quantitative? However you want to say it. Okay. The one that involves standard deviation because they gave me standard deviation, right? So, margin of error. We're going to use 2 sigma divided by square root of n. 2 times, what is sigma? 54. divided by square root of, what's n? 450.
450. 5.
So 2 times 54 is 108 divided by square root of 450. We're definitely talking calculator here. Now, okay, I have 2 decimal places written down in mine. I know earlier I went whole number, but that's because I was going to be adding and subtracting to a whole number. They're just asking me margin of error here. I don't have a number I don't have a mean or anything I'm going to be adding or subtracting it from. So I have 5.09. Okay. With that in mind, when you express your answer, it is very likely that they'll have you say that the margin of error is plus or minus 509. I don't remember how Savas goes about this. I really don't. Okay. But the idea is that that can go up or down, right? So margin of error, plus or minus. That is a funky 5. Let's try that again. 5.09. Okay? Okay. Now, think about this, but then you can also use the one we just did as a, one that you can play around with. Suppose the sample size was decreased. So suppose we made the sample size smaller. How would that affect the margin of error?
It would decrease.
It would what?
The margin of error would decrease.
If the sample size decreases, then sample size is in the denominator, right? So sample size decreases. That means you're going to be dividing by a smaller number.
Oh, it's going to go up.
So your margin of error is actually going to go up. And as I throw in a number smaller than 450 into your formula. Okay? Take 400, take 200, take, any number smaller than 450. The idea is a smaller sample size. So you sample or test sample or test less. The less you test, that's going to make your margin of error higher. Now, think about it. That makes things, margin of error being higher is going to make things less accurate. So that should sound a little logical, right? We've talked about the idea that the bigger sample size, the more accurate. The smaller sample size, the less accurate. And so decreasing the sample size increases the margin of error. Decreasing sample size increases margin of error. And that's going to be true of either formula. It's not just one formula or the other. That's going to be true of either formula. Okay? Okay. Your lesson 11.5 in Savas. I don't remember how many questions are, to be honest, at all. Okay? So, 11.4 homework scores went in the grade book last night. Okay? So, some of you have not caught up on 11.3, 11.4. Now you have 11.5. Get caught up, right? We've got one more lesson in this chapter, or this topic. That's 11.6. We'll talk about it tomorrow and Monday. Okay? Looking at chapter test at the end of next week, I'm thinking. I haven't done my lesson plans for next week, but I'm guessing that's how it's going to work out.